The example in this video is kind of a classic, I guess you could say. It appears over and over again in various textbooks. An open top box is made by cutting small congruent squares from the corners of a 12 by 12 sheet of tin and folding the corners up. What dimension should the box be to hold as much as possible? And now we're in it. Unlike the previous example, we're not given any equations to work with. We're just having a situation described to us and asked to maximize something. Let's start. This is good advice the textbook gives by trying to picture what's going on. We have a 12 by 12 sheet of metal, and we are cutting squares from the corners. Then that gives us 4 flaps. A flap here, 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 here. We take those, we fold them up, and when we fold all 4 of them up, we get a box, and we'd like that box to hold as much as possible. In other words, we're trying to maximize the volume. So the volume of a box is the length times the width times the height. One of these is the width, the other is the length. This is the height. So we don't want 3 variables, we want 1 variable. Let's try to do better than this. First of all, I know it doesn't really look it in the picture, but we started with a square and we cut these squares out. This inner shape is a square. So the width and the length are equal. And we can get this down to 2 variables. Let's try to get it down further to 1. We're most directly controlling how big these squares we cut out are. So let's try to make this be our variable. If this is going to be our variable, we'd like to get rid of this W. Is it possible to rewrite W in terms of H? Now here's W, here's H. here's H, and a piece of information we haven't used yet, that the length of that side is 12. So W plus 2H equals 12, and W equals 12 minus 2H. We take this and we plug it in here. And I should probably emphasize, if I'm going through this problem fast, I must have done this example 20 times by now at various points in my mathematical career. These steps are not necessarily obvious, and it's very normal to have to spend a fair amount of time on an optimization problem. So please don't feel discouraged if some of this stuff is not immediately jumping out to you. It, again, is only immediately jumping out to me because I've done this example before. The volume, then, is 12 minus 2H squared times H. And we're trying to maximize this. Let's take a look. Here's what the graph looks like. Let's get rid of the extraneous negative stuff. And you might think momentarily that I've thrown you a trick question. This graph doesn't have a maximum height. It just keeps going up forever, a maximum value. It just keeps going up forever. However, looking back at our paper, width is 12 minus 2H, and the width has to be a positive. That tells you that H is less than 6. So going back to Desmos, I'm not really trying to trick you. H is between 0 and 6, and this is our graph, and it really does have a maximum. That maximum is the only critical value between 0 and 6. So let's go looking for it. To find the critical value, we need the derivative of this thing. Probably the easiest way to do this is going to be to FOIL this out and then distribute. Let's see, is this correct? 12 times 2 is negative 24h. It happens twice, so negative 48h. 12 squared, negative 2h squared. This looks correct to me. And now we can take the derivative without using the product rule or anything like that. I'm going to write this in a different order as I take the derivative. This will give us 12h squared minus, let's see, minus 96h, 48 times 2 plus 144, and we're looking for the critical values. We're setting this to 0. If I'm going to use the quadratic formula, I'd like for my numbers to be as small as possible. We can divide both sides of this by 12. When I divided this by 12, that's still h squared, of course. And this might factor, as a matter of fact. I talked about using the quadratic formula, but we are actually spared that. So there are 2 critical values, one at 2, the other at 6, but 6 is no good. H has to be less than 6. And remembering what we saw when we graphed it, this really does represent an absolute maximum. Making sure to actually answer the question, we ask about the dimension of the box. If H is 2, W is 8, and L is 8. So we should create an 8 by 8 by 2 inch box in order to maximize volume.